okay? So the PACF is called partial autocorrelation function. But before we go into the PACF plot, I'm actually going to have a review of what we did on ACF plot that we did yesterday, so that you'll be able to know the difference between the ACF plot and the PACF plot in statistical in time series analysis. Okay, so I was trying to show you these are the review of the ACF plot. And of course, the essence of the ACF plot is just for us to decide to be able to identify the appropriate time series model. Okay. Now, when you take a look at what I have here, most of the correlation here is within 0. Okay. Can you see that now? Because this is a line. Look at the dotted blue line and the dotted blue line right here. And you're actually going to see that they all fall within. The only one that should be outside that, okay, of course, it's going to be this. So of course, the reason why, because at like 0, okay, it's actually going to be 1. I think you know that. So that is why this is telling us a white noise, okay, because you could have a model that is a white noise. I told you the other time, a white noise model is a model that cannot be used for prediction when a time series model is an entirely white noise. Okay, you can use that to make prediction, okay, because it means what is going to happen next. It's actually going to be a surprise. You can't really tell, okay? You can't tell whether it's going to be high or it's going to be low or it's going to be positive or it's going to be negative, okay? In a situation where you get something like this. I'm talking about when you get something like this. Now, when you take a look at this one right now, you're actually going to see that these are outside, you can see all of them. They are, majority of that are outside the boundary, okay? And you know what? They are decaying, okay? They are decaying, okay? And they are all positive. So that is that. And that actually, so that could be AR1, okay? That could be AR1. And of course, C1 has to be greater than 0. You know what I mean by C1? That's going to be the contribution of the autocorrelation, okay? So that is what this is actually talking about. But when you take a look at this one, this is going to be a mix-up, okay? Got some negative autocorrelation value. You also get some positive autocorrelation value. So that was why we said alternate between positive and negative values. Can you see that now? And in a situation where you got something like that, so the C1 is actually going to be less than 0. Okay, so if you take a look at the 3 right here, the 3 ACF plot that we're talking about right here, these are the ACF plots of some time series models. Okay, of some time series data. I'm not talking about the ACF plot of residual. I'm not talking about that one. There's a difference between the ACF plot of time series data and the ACF plot of residual. The ACF plot of time series data is just for us to be able to figure out what is the appropriate time series model to use. I'm going to say that again. The ACF plot that we're trying to do right now, because these are the ACF plots of some time series data, they are basically just to identify an appropriate model, okay? So this is different from the ACF plot of residual. The ACF plot of residual, okay, we actually do that for diagnostics, okay? When you want to actually do what I call model evaluation, model diagnosis, where you are trying to test your model before you use the model for prediction, just like what I did yesterday, okay, when I used the Google stock price example. Of course, the ACF plot of that one will be it's going to be the ACF plot of the white noise, of the ACF plot of residual. But the one that I'm talking about right here are the ACF plot of the time series data. Is there anyone who want to ask question based on this review before I go to the next slide? Is there anyone? Can you guys hear me clearly?
Yes.
Hey, I want you to, feel free with me, ask question, okay? If there's any area that you don't really understand, okay, please ask question, okay? I'm ready to go back, as far as I'm concerned, there is no question that is stupid, okay? Every question, as far as I'm concerned, is good. Okay, having understand that now, I'm gonna go to the top slide. So I'm going to go to the top slide. Okay. If you remember yesterday, I walk you through autoregressive model of order one, and at the same time, I also walk you through the ACF plots. Now I've reviewed the ACF plot with you right now, and the next thing that I actually want to review with you is AR, autoregressive model, okay, of order one. Now, I told you the AR1 means first order of AR, okay? Now, if you look at what I have right here, this is basically uh, the the population model for the AR1, okay? So this is the first order AR model, okay? And I told you what you have right here is the mean, okay, is a theoretical mean, okay, the population mean, okay, and C1 right here, of course, is the parameter, okay, you can see the C1 now, okay, so and this WT is actually a white noise. Okay, and I said another way to write this is to put it in this form, okay? And when you take a look at this in this form, this is more or less looking like, uh, the linear regression model, okay? Can you see that now? So, you know what? The C1, the C0 is more or less like intercept, and the C1 is necessarily going to be a correlation value, okay, which actually explain, connection between the current value of the series and the immediate past. I think you can see that now. And this guy right here is a white noise. And of course, when you specify a model like this, you need to be able to tell us the distribution of the white noise, okay? So this is very, very crucial, okay? So this is actually trying to tell us that the white noise actually, and the residual in the model actually is a white noise, and it's actually distributed IID normal with the mean zero and the variance. Okay, so the properties, I also remember I walk you through the properties of stationary AR1 population model. And you know what and what you need to figure out those properly, this is how to get the mean, how to get the variance, and how to get the autocorrelation value at any given lag. Okay, so of course, these are theoretical formula, and of course, that the C1, the absolute value of that must be less than 1, okay? So I think you know that. Okay, so coming from the ARO of order 1, okay, did you know that we can actually go to the ARO of order 2, ARO of order 3, and so on like that? There are different, ARO model that, within the autoregressive model, we got levels in terms of the order, okay? So, and of course, what we mean by ARO of order 1 is when I'm only looking at the relationship, where I actually want looking at the relationship, building a model, building a time series model, trying to figure out relationship between the current and the immediate past, okay? That's exactly what we're doing. But do you know that under the arrow of order 2, we can look at the relationship between the current and the past, okay? And we can continue to go like that, okay? It's like going backward, okay? So the general one, I'm actually going to call it A arrow of order P, okay? Depending on the order that you actually want to talk about. Okay, if we now want to write a general formula for the A arrow of order P, okay, of course, if you take a look at what I have right here, this is for order 1. If I want to extend that to order 2, so what I'm actually going to be doing, if you take a look at this spot right here, you can see this is C1, yt minus 1 minus mu, and I'm actually going to have it another one that's going to be C2, yt minus 2 minus mu, and so on like that, okay? So then plus my white noise, okay? So this is the A arrow of order P, okay? And you know what? My white noise, WT, which is the white noise, this is the distribution, okay? So what I'm trying to show you right now, because an examiner can ask you to write the AR model of order 2, order 3, order 4. So if it is order 1, it's actually going to be this. If it is order 2, you're actually going to stop right here, okay? You're going to go all the way up to this place and you're going to put plus WT, okay? If it is order 3, you're going to do all the way to plus C3 into Y, YT minus 3 minus mu then plus WT, okay? So what I'm trying to tell you right now, this is the general formula for the A arrow of order P. Because it is not all the time that the A arrow of order 1 may be appropriate, okay? And that is the reason why we may actually want to consider different orders, okay? And try to compare them, okay? Which of the order is the best for the data under investigation, okay? Now, so like I said, it's either you write it general, you write it in this way, or you write it in this way. If you look at it, this is looking like a multiple linear regression, okay? If you remember, it's looking like a multiple linear regression. You can see the number of regressors. You can see these are the C0, the C1, the C2, and so on like that, okay? They are acting like a parameters, okay? Like a B0, the B1, and so on like that. Okay, let us now specifically study, look at model 1 right now. The model 1 right now is AR of order 2. Take a look at that. It is AR of order 2, though the intercept is missing in this model. It is not all the time. They may have intercept or not. There's no problem about that, okay? So this is C1 and this is C2, okay? So this is like, I'm trying to look at the if let me say if this is the Google price, is the price of the is the Google price of a stock, okay? If this happens to be the price of a stock, okay, the current price of a stock, then this is going to be the immediate pass, okay? And this is a past pass, okay? It's just like if today is as today is Thursday right now, okay? So if this is the price of the stock today, okay, then we're trying to say we are relating that to the price of the stock yesterday and the price of the stock 2 days ago. Okay, that is when the unit of time is in day, okay? That is when we're talking about daily. It could be monthly, it could be yearly, and so on like that, okay? So now this is an AR of order 2. And you know what? The variance of the white noise is 0.16, okay? When you specify model, you actually need to specify the distribution of the white noise. Okay, if that is the case, number one, in part of the multiple choice in exam, okay, you may see a question like this in the multiple choice where examiner is actually going to ask you what kind of model is model 1, okay? Of course, if you want to choose that, this is the ARO of order 2, okay? Can you see that now? Is there anyone who doesn't understand why I choose ARO of order 2? Is there anyone? Are you guys hear me?
Yes.
Yeah.
Okay, so does that mean everyone? Does that mean you guys are very good, right, with what I just explained right now?
Yes.
Okay, thank you so much. So this is uh autoaggressive model of order two. Okay, I think you can see that now. Okay, so that is why we select B. Okay, another exercise: complete the R code to simulate 100 observations from model 1. You remember yesterday I walked you through how to simulate observation from a time series model, but this time around what we used yesterday was ARO of order 1. So how can we simulate from AR of order 2? Okay, I'm actually going to walk you through that right now. Now, let me tell you this. Do you know in exam, in part of the multiple choice, okay, if I write question like this, that look like this, and I actually want you to complete because some things are missing, okay, they are very, very missing, okay. So if you take a look at that, those ones are missing. So the one that are missing is the 0.6 right here and the 0.35, okay, because you know why, this is ARO for that too. This is a population model, okay, this is a population model, okay. I think you get it now. Let me see, I think I get something on my chart. I'm gonna check. Oh, okay, okay, the person just said, okay, good job, thank you for that. Okay, so if you take a look at what I have here right now, if I want to simulate from a model, okay, from a time series model, if I want to simulate data set, so what I actually need to do is to be able to, I need the parameters, okay, and that is what I'm actually going to put right here, okay, and not only that, I also need a standard deviation, okay, but when I come right here, this is the variance, okay, and the square root of the variance is actually going to be standard deviation. So the square root of 0.16 is actually going to be 0.4. And you know what? Don't forget that I said yesterday, I'm actually going to use arima.sim, okay? That's what I'm actually going to use. And the n here is actually going to be the number of observation that you actually want to simulate. Okay, and you know what? You can see that right now, then that is that, okay? Is there anyone who doesn't understand the code? Is there anyone? Okay, so if you guys understand the code, the next thing that we actually want to do right now uh, is to be able to go into another exercise. And this time around, the exercise here is, when you when you have two different data set, I'm sorry, excuse me, when you have two different models, like this is a model one, and this is another model, okay? When you take a look at this guy here, this is a arrow of order two, right? And when you take a look at this guy here, this is AR of order one, okay? Now, these two models, okay, we want what the goal here is just to be able to obtain the ACF plots, okay, of the simulated time series data from these two model, okay. So, and I'm going to show you right now. Okay, now take a look at that. If you look at what I have right here now, if you look at what I have here, this is for the model 2, this is for the AR1, and this is for the AR2. Okay, so you know the code to be able to do that. Okay, I showed you yesterday for AR1. You're also going to use the same code for the AR2. Okay, but you know what? Do you know that you can be given the ACF plot, autocorrelation function plots, for two models? And you know what? They're actually going to ask you to identify which model has a particular ACF plot. And that is the reason why I put it right here. Determine which ACF plots belong to which model, okay? And part of what I'm actually going to be walking you through today is just to be able to tell you how you can actually identify, you know, the ACF plot corresponding to a particular model. And you know what? I told you yesterday the meaning of the, how to figure out the ACF plot manually and using the code. The ACF plot is just the plot of the autocorrelation, okay, at various lag. I think you get it now. Okay. Uh, so another thing that I'm actually going to talk about is, so how do I know that this is for the model 2, and how do I know that this is for the uh, model 1? Now, there is something that I want you to remember. If you take a look at this guy, this guy is going to be C1, right? It's going to be C1. I think you know that. Okay, if it is going to be C1, you know that if you look at this ACF plot and this ACF plot, you're going to see that at lag 0, okay, at lag 0 is actually going to be equal to 1. I think you know that. And at, any ACF plot at lag 0 is actually going to be 1, okay. Now, when you take a look at this is actually corresponding to 0.6. Can you see that now? It's corresponding to 0.6. Can you see that now? But when you take a look at the first one right here, okay, when you take a look at the first one right here, you're actually going to see that this guy here is more than that. I think you can see that now. Okay, can you see that now? So because of that, you're actually going to say that, okay, this guy here is for that model. But we have other ways, okay, to be able to figure that out. But another way you can use to figure that out is that if you take a look at what I have right here, you're going to see that this guy is positive, right? This is a 0.6, okay? And you actually expect, you know, to have, the the value should not be significantly, it shouldn't be negative, okay? You shouldn't have a negative values of the autocorrelation, because it should be strictly greater than 0, okay? As you can see right here. But you know what? For you to be able, what I'm doing right now that I'm trying to say, this is just using a visual way, just a visual way to do that. So this is necessary, but not sufficient. But do you know, if I want to answer a question on what am I going to do if I want to know which of these particular plots, which of the ACF plots belong to any of the model, okay? If I want to know which ACF plot belong to which model, that for me to be able to answer that question, then I need additional plots. And that very plot that I need is what that's going to be our focus in today's lecture. Our focus in today's lecture is a PACF. PACF is partial autocorrelation function plot. And that is the reason why, and I answered the question right here, and I said, if I really want to know, if I want to answer the question, which ACF plot belong to which model, then I'm actually going to use, we need a new tool, which is different from the one we have been doing. We need what we call a PACF plot. And that is the focus into this lecture. Now you can see that before going to the PACF plot, I need to first systematically review, okay, to start from, just to walk you back from where we actually started from and to know why we find ourselves here, okay. We find ourselves in a situation whereby we got two ACF plots, and you know what, we actually want to figure out which of the model actually have a particular ACF plot. And to be able to answer that question, we need a PACF plot. Okay, so I want to us to review model 3 right now. If you take a look at this model right here, okay, which is a arrow of order 1, okay, this model, okay. Now we you're going to see that the autocorrelation, okay, at lag 2, okay, is going to be equal to this. Why is it going to be equal to this? You know, I gave you a formula the other time. I'm going to, let me see, let me walk you back. The theoretical formula. You actually, okay, take a look at that right here. It is C1 raised to power K. Okay, so this is, you know, for AR1, you can actually determine the autocorrelation at any lag. Okay, so at K lag. So all what I just need to do is to raise the C1 to the number or to the order of the lag, you know, the lag that I'm actually talking about. Okay, so what I'm trying to talk about right now, given model 3, if I want to get the autocorrelation at lag 2, okay, what I'm actually going to do is just to square that, okay, so at lag 2, so, and that autocorrelation is equal to this. So what I'm trying to talk about here is that the correlation I'm just talking about, yeah, using the model right here, using the idea of the model right here, I'm just talking about correlation between the YT and the YT minus 2. So this is a correlation at lag 2. Okay, that is a correlation at lag 2. But let me tell you something. I cannot go. Is it possible if I'm looking for the connection between, like today is Thursday right now. Okay, today is Thursday. Oh, sorry. Today is Wednesday, if I'm right. Oh, sorry. Today is Wednesday. Okay. Um, Let me see. Is today Wednesday or Thursday? I need to check. Can somebody confirm that?
Wednesday.
Oh, is it?
Wednesday.
Oh, Wednesday,
Wednesday.
right? Okay, thank you. Because I have a lot of things in my brain. Okay, thank you for confirming that. Today is Wednesday. Now, if today is Wednesday, let's say for instance, I know the price of of that stock today. Not only stock. Let's say for instance today, if I happen to be a manager of a grocery store, maybe if I happen to be a manager of a Walmart right now, and maybe the I know my revenue for a particular day, okay, and if I were to look at the connection between my revenue, let's say for today, the revenue for Wednesday, if I want to look at the you know, the contribution of the revenue for Monday. You know, Monday is 2 days ago, right? Okay, so uh, there is no way I will be able to do that without passing through Tuesday. So is there a way I can get from Monday to Wednesday without passing through Tuesday? That is not going to be possible, okay? So if I want to go from Monday to Wednesday, I must have passed through Tuesday. And that's exactly, you know, if you take a look at what I have here, uh, I'm not trying to look at the correlation between, you know, this is like Wednesday and this is like Monday. Of course, I know if I want to do that, I need to pass through Tuesday, okay? This is like Tuesday right now. Can you see that now? So, so this is the current, this is the immediate past, and this is the immediate past, okay? Now, so what I'm trying to tell you is that the correlation could be decomposed into two parts, and I'm actually going to show you right now, because the correlation that I'm trying to find right here is just the connection between the current value of that and the, you know, the two, you know, the immediate, I mean, sorry, the past, okay? And you know what? This is going to be the in between, okay? I think you know that. Okay, so what we are trying to talk about right here is just talking about the direct influence of YT minus 2 to YT, okay? What is the direct influence of what I made on Tuesday, sorry, on Monday, to what I'm going to make on Wednesday, okay? So that's what I'm talking about right here, okay? Now, if I have that one, of course, you know, I must pass through. There's going to be a day in between, right? I'm actually going to pass through Tuesday. Okay, if I want to go from Monday to Wednesday, of course, I must pass through Tuesday. Okay. Now, passing through Tuesday, it means I also need to look at the connection between Tuesday and now. Okay. I need to look at the connection between Tuesday and now. Okay. That's exactly what we're talking about there, okay? And that is the reason why I said this guy here is going to be influence of yt minus 2 to yt through yt minus 1, okay? So that is exactly what we, and that was why I said that that correlation could be decomposed into two. That's exactly what I'm talking about. And you know what? And in a situation where you are looking at that, okay, then you're going to be talking about the partial autocorrelation at lag 2. Okay, so the partial autocorrelation at lag 2 is 0 for mode 3. Now, why is partial autocorrelation at lag 2 is 0 for mode 3? Is 0 for mode 3 because when you take a look at mode 3, you're going to see for mode 3, okay, we only have the order here is of order 1, okay, is of order 1, and if it is at order 1, then we expect the partial autocorrelation, you know, for at lag 2 to be equal to 0. Okay, we expect the partial autocorrelation, though the autocorrelation is 0.8836. But when I say partial autocorrelation, the partial autocorrelation should actually be 0 for that. And the reason being that the yt minus 2 cannot influence yt except through yt minus 1. What I'm trying to say, what I have as revenue on Wednesday, the revenue on Monday cannot just influence my revenue on Wednesday without going through the revenue for Tuesday. And that is the reason why the yt minus 2, which is a Monday here, cannot influence, Wednesday except through Tuesday. So if that now happen, so when we say cannot, then that is the reason why the partial autocorrelation at lag 2 is actually equal to 0. Okay. Can somebody? Is there anyone who want to ask question? Is there anyone who need clarification on the way I've explained this right now and the way I've discomposed that? Okay. Is there anyone? Okay, somebody say yes, a bit more clarification, please. Okay. Yeah, this is what I'm trying to talk about. We actually want to compute partial autocorrelation, okay? As we have autocorrelation, we also have partial autocorrelation, okay? And you know what? If you take a look at the model that we're talking about right now, we are trying to look at the connection between the current and the immediate past. And we now said that is the essence of the model right here. But you know what? We can also talk about the correlation. You know, and you know that correlation at lag 1. The correlation at lag 1 is a 0.94. A 0.94 implies that immediate pass explain more of the current. Okay, immediate pass explain more of the current. And if I were to look at the correlation between the current and past, you know, past, okay, then I expect the correlation to go down. I expect the contribution of past to the current to be smaller than the contribution of immediate pass to the current. Okay, and that is the reason, if you take a look at that, you have a 0.8836. But you know what? This is a correlation value, but what we actually want to get right now is to be able to talk about the partial autocorrelation. When I say partial autocorrelation, okay, the partial autocorrelation, we normally want to use that in a situation where the lag is more than 1. If the time series variable have, you know, the lag apart, the distance apart, if it is more than 1, in this case, the distance apart is more than 1. These are two lag apart. Now, if they are two lag apart, what I'm trying to tell you right now, if they are two lag apart, there is no way I can measure relationship between yt and yt minus 2 without going through yt minus 1. And that was the reason why I was asking you the other time about today that, okay, if I want to look at the connection between Wednesday, today is Wednesday, and Wednesday and Monday. This is more or less like what I recorded on Wednesday, and this is what I recorded on Monday. Okay, and I said there is no way you can do that without the influence of Tuesday, because Tuesday is a day that comes between Monday and Wednesday, and that's exactly what we're trying to talk about. That in that situation, the partial autocorrelation at lag 2, okay, is actually going to be 0 for this model. It's actually going to be 0. And the reason why it is 0 is because you can only measure the influence of past pass on the current, you know, by passing through the immediate past. And that is the reason why we said the yt minus 2, which is the immediate, which is a past, cannot influence your current except through the middle, except through the immediate past. That's exactly what we're talking about. Does that student now understand that now? The student has said, as you explain, that you need more clarification. Okay. Okay. Thank you so much. The student said, yes, it helps. Okay. If that is the case, then I now want to go general. Okay. I actually want to go general now. Okay. Now in general, the autocorrelation function, the ACF at lat K, is the correlation between the YT and the YT minus K, okay? This at K distance apart. Now, that can be decomposed. The other time we decompose, we actually decompose YT and YT minus 2 as this, right? Okay, we decompose YT and YT minus 2 as this, right? And we got something in the middle, right? Now, we're going to do that for the general one. Now, for the general one, if I want to look at the relationship between the current and so many lag ago, look at it. So maybe, for instance, if I'm talking about monthly data now, if I'm talking about monthly data, maybe I want to compare what I recorded in December, okay? And I want to compare that with what I recorded probably in January. Okay, there's a very long distance between December. I'm talking okay, somebody is going to tell me which is because some December and January are close. I'm talking about, okay, because somebody is going to say that, okay, December 2019 and January 2020, they are very close. No, I'm talking about January and December of the same year. The January and December of the same year are very far from each other. I think you know that. If this is, let me say this is December of 2019, and what I have right here, sorry, if this is January 2019, if this is January 2019, and what I have here may be December 2019, okay? Of course, December 2019 is more current, right? December 2019 is more current than January 2019. Okay. Now, if I want to look at the correlation between YT, okay, and YT minus K, then of course I can only do that, by I mean I cannot do that without the influence of this. You understand what I mean? So without the influence of this, I cannot do that. Okay. So now, if you take a look at what I have now, I'm trying to get the direct influence of these two. Okay. And if I'm trying to do that, and that was why I call it direct influence. Okay, so if I want to look at the direct influence of what I got, my revenue, okay, what I realize in these two period, okay, if I want to get that, I can only do that, you know, uh, with the influence of the one that come in between. Okay, so what I've been able to do, and that was why I call that influence of yt minus k to yt. Okay, through the yt minus k plus 1. So when I talk about the influence, now I'm talking about this guy here up to this. Okay, there is no way. So what I'm trying to talk about is, if this is January 2019, if this is a revenue that I realize in January 2019, and this is the revenue that I realize in December 2019, then if I want to measure the direct influence of this on this, then you know what? What I recorded in February 2019, in February 2019, March 2019, all the way to November 2019. Okay, I can only measure the direct relationship of this one with the influence of that. That's exactly what I'm talking about. Okay, so and that was why, so that has been broken down into that. Okay, and you know what, it is only when you have that that you will now be able to obtain your partial autocorrelation. Okay, that is when you can be able to obtain your partial autocorrelation. Okay, now in time series, a partial autocorrelation at k measures the direct influence, okay, the direct influence of yt minus k to yt. I'm talking about this, okay, is direct influence. Okay, we are not going to be looking at that one at a time. It's going to be the direct influence. What is the direct relationship, between what I realized in the January 2019 and December 2019? Okay, so that is what the partial autocorrelation is actually talking about. Okay, in other words, it is a correlation between these, okay, that are k distance apart, but you can only do that. You have to put into consideration, I can only measure my revenue, okay, I can measure my revenue, okay, the direct relationship, the connection between what I made in January 2019 and December 2019. I can only do that, by passing through the February, the March, up to November 2019. So I have to control for that. So in a situation where you are trying to find a correlation, okay, and you control that, then you are doing partial autocorrelation. But if you just doing that, like somebody is going to ask me, if I don't control that, okay, if I don't really control that, if I do that already without controlling that, then I'm doing autocorrelation. But if I'm putting into consideration that if I'm controlling that, then I'm doing partial autocorrelation. Now, let me just remind you of this. Let me remind you of what we've done in linear regression. You're going to see the connection between this and linear regression right now. In a simple linear regression where you have one predictor, okay, in a simple linear regression where you have one predictor, okay, let's say the predictor is maybe you are looking at the effects of advertising on sales. Okay, if advertising is a predictor and sales is the response, okay, if the only predictor you have in your model is advertising, then it means you are looking at the direct contribution of advertising to sales. But in a situation where in your model you got more than advertising, maybe you have advertising is a predictor, and maybe another thing that is a predictor may probably be location. Okay, may probably be location. Okay, location of your store. Okay, then if you want to measure the main effects of advertising in that model, you got to control for location. Okay, you need to control for location. Okay, so in multiple linear regression model, when you are trying to take a decision on a particular predictor, okay, then you are trying to say, after adjusting or after controlling other predictors. And the same thing also happen here. If you take a look at this, if I have a direct correlation between yt and yt minus 2 without controlling for yt minus 1, then what I just have is autocorrelation. But in a situation where I actually control for what come in between, okay, when I actually control for what come in between, okay, then I'm actually talking about partial autocorrelation. But there is something I want to ask you right now. Somebody is going to tell me, why is it that at lag 2, the partial autocorrelation equal to 0 for this model? Because, okay, let me ask you that question now. Extra credit. I want to ask question now. Why is it that the partial autocorrelation equal to 0 for this model? Can somebody tell me? Why is it that the partial autocorrelation equal to 0? I want you to tell me from the actual sense, okay? Why is it that I'm talking about this model and I said at lag 2, I said the partial autocorrelation equal to 0. Why? Can somebody tell me for extra credits? Are you guys hearing me? Are you guys hearing me? Are you guys hearing me? Oh, yes, okay. Yeah, somebody said it is not a predictor. Yeah, what is not a predictor in the model? Can you tell me? You said it is not. Somebody who said it is not a predictor in the model. So what is not? You need to explain that. And somebody said, because yt minus 2 was autocorrelated. What do you mean by that? You mean you said yt minus 2. Can you simplify that? Can you clarify? Somebody said it is not in the model. Oh, good job. I'm giving it to somebody who said it's not in the model. Yes. So somebody who said it is not in the model, get it right. Because if you take a look at the model right here, I'm only talking about current and the immediate past. And there is nothing that comes between the current and the immediate past. If I'm considering daily, okay, and if I'm considering Wednesday and Tuesday, if I'm considering Wednesday and Tuesday, there is no day that come in between. Okay? There is no day that come in between Wednesday and Tuesday. It is only when I'm talking about Wednesday and Monday. Of course, for Wednesday and Monday, of course, there's going to be a day that come in between that. And that day is actually going to be Tuesday, okay? So I'm actually giving it to somebody who said it is not in the model. So that person that said it is not in the model should send a message to me for extra credit. So, and that is why if you take a look at the model 3, okay, because we're talking about, you know, the current and immediate past. Of course, and there is nothing in between them, okay? The partial autocorrelation at lag 2 will be 0. Okay, I haven't know that now. Now, I now want to go into partial autocorrelation plots. We're going to go into partial autocorrelation plot right now. And I told you the partial autocorrelation, PACF, is what we call a PACF, and partial autocorrelation, we call it partial autocorrelation function. And you know what? The PACF plot gives the estimated partial autocorrelation value at each lag, starting from lag 1. Okay? we actually going to start from lag 1. Okay, now we're going to see the plot right now. Now the plot is actually going to look like the ACF plot. It's going to look like the ACF plot. But you know what? It has to start from the difference between, take a look at this. Okay, this does not start from 0. But if you look at the ACF, okay, the ACF, the autocorrelation plot will start from 0. Look at that. Can you see 0 right here now? All the ACF plots, they're actually going to start from 0. Okay, because when they start from 0, that is when the autocorrelation is actually going to be 1. That's when you are considering the same set of variable. Okay, now that is how you can actually detect, you can actually distinguish between the ACF plot and the PACF plot. So now if you take a look at what I have right here, you actually going to see the first one. The first one is starting from lag 1. It's on lag 1. And of course, if you look at this model, okay, if you look at this model, of course, the C1 is 0.6, right? And that is the reason why this one is, we actually go to 0.6, because it's that correspond to lag 1. Can you see that now? So, and when you take a look at that, then we said for AR1 model, partial autocorrelation are equal to 0 for lag greater than 1. Now, any lag greater than 1, that is, after this lag 1, you're actually going to see every other one right here, you're actually going to see they are binded. You know, I told you the other time about this blue. It is only when they go over the blue line that you're actually going to see the correlation is greater than 0. Okay, you can see right what you see right now. All of them, they are within the blue dotted line. Okay, and let me tell you something. Any lag greater than 1, okay, when you are talking, because when you are talking about right here is an autoregressive model of order 1, you are only talking about relationship between the current and the immediate pass. Okay, and you know what, there is nothing in between immediate pass. There's nothing between the current and the immediate pass. Okay, so because of that, you're actually going to say any lag greater than 1, okay, the partial autocorrelation will be equal to 0. And you take a look at that right here. They are binded. None of them, none of this line actually go beyond the blue dotted line. Is there anyone who want to ask question or who need clarification? Is there anyone? Can you guys hear me? Okay, somebody say yes. Okay, so if that is going to be the case, now you understand what we mean by that. So this guy here is a PACF value estimated at lag 1, okay? So I think you know that now. Now, the next thing that we want to talk about now, since you know how the PACF, we're actually going to start from lag 1. Now that you know the difference between the ACF and the PACF, now let's talk about two different models, okay? And we want to talk about what is the theoretical provision, okay, for what the partial autocorrelation is actually going to be. Now, let me tell you that for AR1 model, the partial autocorrelation are equal to 0 for lag greater than 1. Automatically for AR2, then for lag greater than 2, the partial autocorrelation will be equal to 0. Does that make sense? Then it means for AR3, okay, for AR3 model, it means for lag greater than 3, the partial autocorrelation will actually going to be equal to 0. That's what we're talking about. Okay, now let us now have two models. Okay, we got the A arrow of order 2 and we got the A arrow of order 1. Okay, and you know The reason why we find ourselves in this situation is just for us to be able to use a PACF plot to be able to distinguish the model, okay, to be able to know when I see a PACF, I will be able to know, which of the plots actually represent a particular model, okay. Now, if you take a look at what I have right now, you're actually going to see that, you know, this is a AR of order 2, and this is a AR of order 1. And let me start with this. We have said that AR of order 1, any lag, the correlation of any lag greater than 1 should be 0. Let's see. Look at that. For AR of order 1, at lag 1 is 0.94. But anything greater than that lag, if you continue to go, all these are 0. Why are they 0? Because they are all 0 because they are within the blue dotted line. Can you see that now? So when you see the graph, like when you see a plot like this, okay, you will be able to know that this is the AR1. Okay, I'm able to know that it's AR1 because I know that the autocorrelation at a lag greater than 1 has to be equal to 0. And look at that, at lag 1 is a 0.94, but at any other lag, all the autocorrelation values are within the blue dotted line. But when you take a look at this one now, we expect the autocorrelation of AR of order 2, okay, we expect the autocorrelation, if the lag K is greater than 2, if the lag is greater than 2, like if you are going from 3 and above, they should be 0. But at lag 1 and at lag 2, that will be over 0. Take a look at that, because I'm talking about ARO of order 2, then the first 2 lag. Okay, the correlation of the first 2 lag, we go beyond the blue dotted line. But you know what? Anything from lag 3 and above, the autocorrelation will be equal to 0. So why do I know that the autocorrelation equal to 0 right here? Because all the other one are within the blue dotted line. Is there anyone who want to ask question or who need clarification now? Because in exam, I'm actually as part of the multiple choice, I'm actually going to give you a PACF plot like this, and I will ask you to identify, okay, the appropriate model. So now you know how you can read a model. Do you know that from a PACF plot, I can actually decide, I can actually write this one. From here, I can write this one, I can write this out. From here, I can write this out. Because from here, I'm going to know that, oh, this is a 0.94, okay? I'm going to read that, which is this one. And I know that for AR1, okay, the autocorrelation, of the order greater than 1, we're actually going to be equal to 0. Then I'm actually going to know that this is going to be AR1, okay? And this guy here, so please try to understand that, okay? If there's anyone who doesn't understand how to do that, I needed to ask a question before I move to the next slide. Is there anyone who need clarification? Is there anyone? Now, will I be right if I say you guys are good? Will I be right if I say you guys are good? Are you guys good?
Yes.
Thank you so much. Then I'm gonna move forward now. Okay, so I answered this for you the other time. Now you know for AR3, okay, the partial autocorrelation for for the lag greater than 3 will be 0, okay, for AR3. So which means if I want to generalize that, okay, For autoregressive model of order P, any lag greater than P will be equal to 0. I mean, for any lag greater than P, the partial autocorrelation will be equal to 0. I'm going to say that again. If I want to generalize that, okay, so if I have autoregressive model of order K, okay, for K if I have autoregressive model of order P, okay, so if the number of lag is greater than P, okay, the partial autocorrelation will be equal to 0. Okay, so the next thing that I actually want to do right now, I want you to be able to see two different stuff, okay? We got the two different models. I'm just trying to show you the ACF plot of the two models and the PACF plot. I just wanted to see the difference between the ACF plot and the PACF plot. Okay, as you can see right here, this is the ACF plot of this model, and this is the PACF plot. And like I said, the ACF plot, of course, the lag is going to start from 0. Can you see that now? And in the PACF plot, you're actually going to start from 1. So don't forget that, okay? So so based on what I've explained so far, this is the PACF plot of this, and this is the ACF plot. So I need you to take a look at that. Is there anyone who want to ask question? Is there anyone who want to ask question? Is there anyone? But let me tell you this. If you see this plot and this plot, okay, you may not be able to identify which of the model the plot belong until you study the PACF. So the PACF can actually tell me whether it's going to be AR1 or AR2 or AR whatever, okay? When I take a look at this guy right here, I know when I have the two lines above the dotted line, and then I know it's actually going to be AR2. And when I only have one line, going beyond the dotted line, I'm actually going to know that is going to be AR1. Because I know outside that lag, every other thing is going to be 0, okay? All the autocorrelation is going to be 0, okay? So that is that, okay? So I think you know that now. Now, there's another thing I want to talk about. If you take in the ACF plot, you're going to see that the autocorrelation is decreasing, right? And if you take a look at the positive side, it's decreasing. The negative side is decreasing. Then we're going to say it's decaying, okay? It's decaying, decaying like decreasing, going down to 0, okay? And when something is decaying and going down to 0, that is an evidence of autoregressive model, okay? Because I told you the other time that we got series of model in time series. We got the autoregressive model, the moving average model, the autoregressive moving average model, the autoregressive integrated moving average model, and so on like that. Okay. Now let me tell you this. If I want to be able to tell on the appropriateness of a model, okay, if I have an ACF plot and if the autocorrelation is decaying, that is an evidence of autoregressive model. Okay, that is an evidence that this is likely going to be an autoregressive model because the autocorrelation function of autoregressive model decay exponentially to 0. Okay, you can see what you're seeing right here. But if I want to talk about partial autocorrelation for a plot to be able to decide on that, then I'm actually going to say what happened if I'm talking about AR2, what happened after lag 2? After lag 2, it's actually going to cut off. This is like cutting off, okay? And that was why I said, when you are using a PACF plot, if for a model to be autoregressive model of order 2, okay, if for a befitting model for the time series model, for the time series data, for it to be an autoregressive model of order 2, then what we are talking about is actually autocorrelation will cut off the partial autocorrelation to cut off after lag 2. That is for partial autocorrelation. So the same thing right here. Let me tell you something. All autoregressive model decay partially to 0, whether AR1 or AR2 or AR3 or AR whatever. All of them partially decay to 0. Okay, but if I want to know which of the AR, is it going to be autoregressive model for that one? Is going to be AR1 or AR2 or AR3? Then the PACF is what I'm going to use, because if it cut for if that thing cut off after lag 2, it means it can only tolerate up to lag 2. It can tolerate up to lag 2 because of the fact that we're talking because it is an AR2. It is an AR2 because I'm only want to talk about 2 distant apart. I cannot use this to talk about more than 2 distant apart, and that is the reason why it's actually going to cut off after lag 2. If it cut off after lag 2, then it's an AR2. So if it cut off after lag 1, you can see after lag 1, it actually cut off, then it is an AR1. I'm going to say that again. You can use the ACF plot to be able to know whether you are working with the autoregressive model or you are working with the moving average model or not. Okay, so if the ACF plot decay to 0, then we are trying to say that is an autoregressive model. But with this, with the ACF plot, we may not be able to tell, which of the autoregressive model is it going to be order 1, is it going to be order 2, and if we really want to know that, then we need to investigate the partial, the PACF. So when the PACF cuts after lag 2, then that is an AR2. When the PACF cuts after lag 1, that is an AR1. When the PACF cuts after lag 3, that's an AR3. When the PACF cuts after lag 10, that is AR10. Okay. Now, how to identify an autoregressive model of order P? I just talked about that right now. This is just going to be the summary of what I just talked about. I said in the ACF plot, the estimated autocorrelation must decay. Okay, must decay partially to 0. Okay, so as the lag increases, you expect the autocorrelation to be coming down. So when the autocorrelation is coming down as the lag is increases, that implies autoregressive model is appropriate for the time series data. And not only that, when the PACF plot cut off, okay, in the PACF plot, the estimated partial autocorrelation will cut off at a particular P. So after that P, then we are trying to say that, oh, that is going to be an autoregressive model of order P. If it cuts off, if the partial autocorrelation cut off after lag 4, if it cuts off after lag 4, then it means an appropriate model within the autoregressive model is actually going to be AR4. Does that make sense to everyone now? That's exactly what we're trying to say. Okay, so in the example right now, so I'm going to revisit ARO of order 1. In the ARO of order 1, the autocorrelation function, okay, when you in R, when you write this one, you're actually going to have a 0.6. Of course, for this second one, okay, when they are 2 distant apart, of course, you know it's 0.6 squared. Of course, you know the formula that we're using right here, right? I showed you before. Now, take a look at the value that I have right here, okay, for this model now. How do I obtain the partial autocorrelation function, okay, for each of that? Now, this shouldn't surprise you because if you take a look at the model, we're talking about a arrow of order 1, okay, we expect to be able to have just partial autocorrelation between the yt and the yt minus 1, because the model is actually focusing on AR of order 1, okay? And because of the fact that there is nothing between the current and the immediate path, then anything outside that is actually going to be equal to 0. And that is the reason why you see that the PACF of yt minus 2, given the model here, is equal to 0, because in looking at this model, the yt minus 2, okay, you cannot be found in this model. So okay, look at the other one, it's going to be 0. Are you guys surprised that is 0? Of course, that's not surprising at all. Okay, I'm actually going to go back to the Google stock price that we were talking about yesterday. And you remember yesterday, we used the data set of the Google stock price between April 22, 2018 and April 22nd, 2019, okay? So we use the data, and you know what? The data set here has actually been adjusted, okay? The daily, we're using the daily adjusted closing price of Google stock, okay? Now, we've been able to, yesterday, I've been able to walk you through how to get the ACF, okay? You know, for that data set, an expert in the equity market may really want to know what is the appropriate autoregressive model that can actually be applied to this data set, okay? So in the process of doing that, of course, we can actually draw the PACF, okay, and so on. Now, if you look at the first one here, of course, this is a time series graph, okay? This is a time series plot, okay? I showed you that yesterday, because the price, this is expected because we're talking about the Google stock price, okay? Because we're talking about there's going to be a lot of volatility, okay? Coming up, going down, coming up, going down, and so on like that, okay? And you know what? The ACF plot, this is the ACF plot. If you take a look at this ACF plot, this actually tells us the correlation, the autocorrelation is decaying, okay? And when it is decaying like that, okay, that actually implies that that could be autoregressive model that may be appropriate, okay? And of course, and that was why I said the last time we fitted an AR1 model, okay? You know what we fitted yesterday, and then check the residual. We check the residual to make sure that the model is a good fit, okay? You know, we do that yesterday. Now, we have the autocorrelation on residual, and we have autocorrelation on time series data, okay? I told you the autocorrelation on the residual is just for us to be able to subject the model to that when we're subjecting the model to diagnostic testing, and that will enable us to evaluate, okay, whether the model is adequate or not, okay? Now, we did that yesterday. Okay, but today for the data set, we want to have the partial or ACF, which is the PACF. Okay, and you know what? The partial ACF will also tell me whether the AR1 is appropriate or not. And if you take a look at what I have right here now, this actually cut off after lag 1. Can you see that now? It's cut off at this is lag 1, at lag 1. Can you see that now? And after lag 1, okay, it's actually so, and that's why I say AR1 is appropriate for this time series. Okay, it's actually cut off. Though some of you will be saying that what about this guy here? Okay, but I told you yesterday, okay, you can see that immediately after this one it cut off, though we have something here. But you know what? Let me first give me 1 second. Let me first tell you that it's not going to be I told you that yesterday there's a percentage, okay, that we can actually tolerate, okay, when I told you something about 5%, okay. So but when you take a look at what I have here after lag 1, immediately it's immediately cut off. That's what I'm talking about. It's immediately cut off, okay? And that is actually indicating that, okay, the AR1 is actually appropriate, okay? Uh, before I go today, I want to summarize what I've done, what we have been able to do. I want to tell you today, I introduce you to what I call a PACF plot. And we need a PACF plot when we are trying to figure out the appropriate model for a time series data. Now, when I have the, uh, you know, different kind of models, we got different kind of models, okay? And if we want to decide on which of the models is appropriate. When I say models, I'm talking about autoregressive model or moving average model or autoregressive moving average model or autoregressive integrated moving average model and so on like that, okay? Now, the first set of models is, now if I want to know, I actually need to obtain ACF. The ACF, okay, which is autocorrelation, okay, I need to have a plot of that, and I've walked you through how to do that. When I get the autocorrelation function, okay, or the ACF plot, and what I'm going to see in the ACF plot is when the autocorrelation decay exponentially to 0, and that will implies autoregressive model, okay. Now, but the question now is, within the class of autoregressive models, okay, which of them is actually going to be appropriate in terms of order, okay? Then I need to do a PACF, okay? Now, on the PACF, if I'm talking about if the autocorrelation, if the partial autocorrelation cuts off after a particular lag, okay, if it cut off after a particular lag, it means if it cut off after lag 1, then it means the autoregressive model for the 1 is appropriate for my data set, okay. And if it cut off after lag 2, then it means ARO for the 2 is appropriate for my data set. So let me tell you something. Like I normally say, we are in a world where we want to have a control, you know, over our environment. So if you want to have a control around the world around us, what we normally want to do is to make sure we model. But the question is, are we using the right model? And that is the reason why we don't get things right at times is because we don't use the right model. Any analyst or any stock specialist or any researcher that is using model, okay, need to be able to investigate and, among the possible number of models, which one is the most appropriate for the data set. Because in the situation where we don't care about that, okay, we actually going to end up using the wrong model. We're actually going to end up using, you know, uh, nothing that is very far from the best. And what do we expect to get from a model that is not adequate? Any recommendation from that model will not see the light of the day. Any policy formulation based on that model will not see the light of the day. And that is the reason why we actually need to investigate. We know situations in real life are kind of stochastic in nature, okay? We know situations are kind of volatile, but let me tell you something. Under uncertainty, we can see model the situation and bring out a sense. But for us to be able to bring out a very good sense of that, for us to be able to have something good out of the model, let me tell you this. I'm going to tell you this now. We have data set, we got models. There are information in the data set, okay? This information remain hiding, okay? It remain hidden, and let me tell you this, it is only when you use the right statistical method that you'll be able to get, the information in the data set. But let me tell you something. The fact remains that even if you use the best model in the world, you cannot extract 100% information in the data set because our model is not perfect. There's always going to be unexplained variation. But you know what? In a situation whereby the unexplained variation behave like a white noise, particularly in a time series model, if the unexplained part, which I call the residual, if it is a white noise, okay, if it is a white noise, then what we are talking about is that our model is more or less adequate. Our model will be able to extract a reasonable amount of information in the data set. That's what we're trying to talk about. But you know what? That actually depends on whether you are using the right model or not. And that is the reason why we're trying to walk you through this. For those of you who is aiming to be a stock analyst in the future, or for those of you who really want to analyze situation in the financial market, for those of you who really want to analyze situation in a very volatile in a very volatile kind of situation, of course, you have to put this into consideration, okay? You have to look at the autocorrelation plot, you have to look at the PACF plot. We do all this for us to be able to identify the right model for the data set. Is there any question do you have for me today? Is there any question? Is there anyone who want to ask question? Okay, I want to thank everyone for attending my lecture today. I hope you guys enjoying it. Until tomorrow again, that I'm actually going to come your way with another exciting topic in time series. Make sure you stay safe and do have a good day. Somebody said, I think I want to read my chat right now. Somebody said, for the final, will we be tested on material that has been covered by the midterm? Now, let me tell you this. Your final exam will be cumulative, okay? But the 60% of that final, okay, is going to be 40% of what was covered in the midterm and 60% of what you done newly. Have I answered your question now? The person that said yeah, okay, so that is that. Okay, bye for now.